demonstration of the screen. This is my presentation. We are interested in the maximal displacement of a catalytic branching random walk. This problem is the problem of the spread of population of particles, bacteria, individuals, genes, fire, or in other contexts, the propagation of fire or epidemic. This problem has been attracting interest of many researchers. It is sufficient to recall the classical work by Kolmogorov, Petrovsky, Piskunov, and their celebrated KPP equation. The works by Sevastyanov, Begins, Darrett, Comets, Popov, Lifshitz, Roberts, Malain, Shi, Bocharov, Harris, Neumann, Zhen, Huang, Zon, Nishmori, Shazava, and others. So the following picture demonstrates how the fire spreads. And we are interested in also the spread of fire or population. We are interested in this border, which we will call by the front of the population.
I'm really sorry. Could you press Ctrl-L to make the share bigger? Yeah, excellent. Thank you.
There are a lot of literature on branching processes by, for example, by Vladimir Alexeyevich Vatutin. Here is his book by literature on branching random walks, survey by Zanshi from Paris, and classical, of course, books by Trenet and others. A frequent assumption in the model describing the spread of particle population is behavioral homogeneity in space. So the behavior of a particle does not depend on its location on the lattice. However, a special approach is needed to investigate the models with spatially non-homogeneous particles evolution. So when behavior of a particle, possible behavior of a particle depends on its location. And we are interested in such a model of catalytic branching random walk on d-dimensional lattice. The main feature of this model is that there the particles may produce offspring at the presence of catalysts only. And catalysts are located at some fixed points of the lattice. Outside the catalyst, the particle performs a random walk without branching. The contribution to the study of catalytic branching random walk is due to the following researchers. Not only them, and others. So let us give a brief description of catalytic branching random walk on d-dimensional lattice. This is a probabilistic model of the particles' population evolution due to offspring production and movement on integer lattice. The particles move on the lattice according to a reducible Markov chain generated by the infinitesimal matrix. So the random walk is time continuous. The particles split at the location of catalysts only. W is the set of catalysts. When a particle reaches a catalyst, it spends their random time having exponential distribution. Then it either produces a random number of offsprings with probability of alpha k. K is the index of the catalysts, or leaves the catalyst with an opposite probability. The new particles behave as independent copies of the parent particle. And we assume that at the initial time there is a single particle on the lattice located at point X. Similar to ordinary Galton-Watson branching process, catalytic branching random walk can be classified as supercritical, critical, or subcritical. This complete classification is given in our paper, in Theory of Probability and its Applications. And it can be expected that only in supercritical catalytic branching random walk, both total and local particle numbers grow exponentially to infinity as time tends to infinity. And the rate of exponential growth is traditionally called Malthusian parameter. In critical or subcritical catalytic branching random walk, the total number of particles does not change after some time and is a random variable in time limit, which might be zero. So it is possible that in critical and subcritical catalytic branching random walks, the particle population does not degenerate, so it survives, but locally it degenerates. So at each point of the lattice in the time limit, there are no particles, but on the whole lattice, there can be several particles which perform a random walk. Here we use some notations. Z of t is a random set of particles at time t. X z of t is position of particle z at time t. We assume that the random walk is space homogeneous. And now we can consider the first case. So I will open some I want to have an opportunity to draw a picture. One moment. No. So we will have three cases. First one. First, supercritical. Super. One moment. I'd like to have more clear explanation. That's why I'd like to fix what we're interested in. Supercritical. This is the first item. Then critical and subcritical. In the first case, supercritical, we have three cases also. First case, light tails. The second case, when the tails of the random walk which perform the particles, which is performed by particles. The second case, when the tails of the random walk have semi-exponential distribution. So the semi-exponential distribution. And the third case, when the tails of the random walk are completely heavy, so semi-exponential distribution is intermediate. case between light tails and very heavy tails. So heavy tails, it means regular varying tails. Regular varying tails. And moreover, we have two possibilities on d-dimensional lattice when the tails regular varying and have different parameters in different directions, and when they have the same parameter, and the latter case is called isotropic case. So we have here we have two possibilities, 1 and 2, 1 and the second, non-isotropic, isotropic. Non-isotropic and isotropic. So now we have such a scheme, and we will consider our new results for according to this scheme. So we are interested in supercritical catalytic branching network now with light tails. Okay, now we can return to the presentation. So light tails, it means that the intensities of the generator of the random walk satisfy such inequality. This function is finite. This assumption is Cramer's condition for the jump value of the random walk. So we suppose that the jump of the random walk satisfies to Cramer's condition. It means that this function is finite. Now we should introduce some sets, and the result is that, you see, it is here, one of the main results. When we consider particles' position, they are denoted by x v of t at time t, and then we normalize them by t and let t tend to infinity. Then in the limit, such a fraction does not belong a special set with probability 1. And the next assertion is that such a fraction does, that there are such particles, you see there exists, and there are such times at which such fraction does not belong to another set Q epsilon with probability 1, but conditionally on the event that the population does not degenerate. So now I'd like to have one more picture to explain this idea. So we have a special set, which we will call by P, propagation front. And we have a set around P O epsilon for epsilon small enough, or epsilon is close to P. So O epsilon is external part. And we have set Q epsilon, which is inside of P, inside of propagation front. Inside. So When epsilon is small enough, then O epsilon is as close to P as possible, and our theorem 1 states that for time large enough, all the particles with normalized positions are in the set, does not belong to the set O epsilon. So they are inside of this set. They are here. So we have a estimate from above for the population, which is a random set. Asymptotically estimate from above. And conversely, when we want to have an estimate from below for the population, for the front of population, for this curve P. So when we normalize positions by when we normalize the positions of the particles by t and then t to infinity, there are only finite particles. There are only finite number of particles which there are always particles which do not belong to the set Q. So they are in the interlayer between Q epsilon and P. So they can be close as P as possible from below. So this theorem has two estimates, from above and from below. And that's why this theory means that if we divide the position coordinates of each particle at time t by t, and then let t tend to infinity, then in the limit there are almost surely no particles outside set, outside the curve P. And under condition of infinite number of visits of catalysts, there are almost surely particles on P. So P is the propagation front of the particles population. It satisfies two, arises in two estimates, from below and from above, for the normalized locations of particles in the limit. The next theorem states that each point of P can be considered as a limiting point for the normalized particles position. So in the limit, it means that in the limit, each point of propagation front is a limit point for some particles with normalized positions. It reveals the density of population in catalytic branching random walks. And the third theorem have one more way to introduce this the set P. So in light tails studied by us. The first paper in this direction was due to Carmona and Hu in 2014. They studied the case of D equal to 1 for one-dimensional lattice, and we generalized their results to multidimensional setting. This paper is published in Stochastic Processes and their applications. And there are methods of the study. We use many-to-one formula, renewal theories, martingale change of measure, convex analysis, large deviation theory, coupling method, and our previous results. And due to the third theorem, we can draw the propagation front, the limit shape of the propagation front. For example, for a simple catalytic branch random walk. So it means that a particle may perform jumps to the nearest points only. So for such a catalytic branch random walk, the propagation front looks like on the picture. When we consider an asymmetric catalytic branch random walk on Z2, then we can get such a picture like a neg. Or such a picture when we consider Poisson-Bernoulli distribution. In a three-dimensional case, we also have something like an egg. So you see that in for light tails, the propagation front of the population. So this is the limit shape of the propagation front is the set P, which we talk about, and it is a convex surface. It is evidently from the pictures. Now we turn to the second case, semi-exponential distribution. So when the random walk, which is performed by the particles, have more heavy tails, not light tails, heavy tails, but not very heavy tails. Semi-exponential, it means that the jump of the if coordinate of the jump of a particle has a tail which can be represented in by such a formula. So you see exponent but in the exponent there is degree gamma between 0 and 1. So such tails are not light but not very heavy. So all the moments exist, but the Cramer condition fails. So this is an intermediate case between very heavy tails and light tails. We introduce normalization for particles. It looks like a regular varying function with such parameters. And we introduced additional assumptions, which are valid, for example, when the components of the random walk jump are independent. We verify this condition for the case when the components are independent and have a Weibull distribution. Each absolute values of positive, negative components have discrete Weibull distribution. It is published in our paper recently in Mathematical Population Studies, International Journal of Mathematical Demography. So we, after normalizing the particle's position, we tend time to infinity and get set a surface P, which is the propagation front. It is given by this formula, and prove similar theorems for semi-exponential distribution similar to light tails. And now we can show pictures. So you see that when the tails have semi-exponential distribution and when the components of each jump are independent or close to independent, then the limit shape of the front looks differently from the case of light tails. So you remember that when we consider light tails, we see a convex surface, but now this surface is far from to be convex. It is star-shaped surface for symmetric catalytic branching random walk, for non-symmetric catalytic branching random walks, and in three-dimensional case it looks something like that. So you see that the heavity of tails of the random walk influences the propagation front of the particle population. It is important that here we assume that the components are independent or close to be independent. However, for light tails, it was not important whether the tails, whether the components are independent or not. Maybe some of you have already guessed that such a difference is connected with large deviations. And you know that for large deviations for random walks with light tails is a special theory, for example, developed and exposed in the book by Alexander Alexeyevich Borovkov, for example, asymptotic analysis of random walks. And the investigation of large deviations for random walks with heavy tails is completely requires completely other methods of study and contains completely different results from large deviations when the Kramer condition is satisfied, and is exposed in the book, for example, Alexander Alexeyevich Borovkov, Konstantin Alexandrovich Borovkov, and the book by Professor Foss and his co-authors, Dmitry Korshunov and Zachary. So you know that large deviations for random walks with heavy tails and with light tails are different, completely different. So it influences on the propagation, on the form of the propagation front for a catalytic branching random walk also. So the third case, heavy tails. Heavy tails, it means regularly varying tails. For us, and it is it is a frequent assumption that heavy tails means regular varying tails. So here you see that the tail is a regular varying function. We also introduce some conditions to be satisfied of surfaces and so on. And we see that in the limit, there are theorems, strict and rigorous, but I'd like to explain in a few words that in the limit we see that after normalization, all the particles population is in the limit, is on the axis of the lattice. It is in the case of independent jump coordinates. So when we consider semi-exponential distribution, we assume that the coordinates of the walk jump are independent. And here we also assume that the components of the jump vector are independent. And in this, and have different, generally different parameters of regular variation. So you see here gamma eta gamma I depends on the number of the vector component. And it's interesting that when the components are independent, all the population is propagates not diagonally wise, but in different directions, but on axis. Diagonally wise, it is very it has very little probability, very small probability that the population will spread diagonally wise, for example. So it spreads in directions along axis. Due to this assumption, independent job coordinates. And that's why it's interesting to compare such results with the case isotropic. So we considered non-isotropic case, independent job coordinates, and now isotropic. It means that all the components of the vector of the jump are connected with the same regular varying function v. So the parameter of regular variation is the same for all components. And in this case, the results is another. There are no pictures, but we may draw it by themselves. So, for example, it's interesting that in the case of heavy tails, the propagation front is no longer a deterministic surface. It's a random surface. And we may only to estimate the probability of that the propagation front is in such, for example, a set. It is a set A, for example.
Ekaterina, now we have time for the questions, but you can continue if you want to finish your talk.
I'm sorry, yes, I thought that we have 40 minutes, but I forget that I should tell only 30 of them. Oh, I'm sorry. Okay, I'll try to finish in several minutes, okay?
Okay.
Thank you. When we deal with heavy tails, the surface is random in the limit arises, and there is a probability that such a random surface is contained in set A, for example. Okay, and maximal displacement of critical and subcritical catalytic branching random walks. So the second case, we finished with the supercritical case, and now critical and subcritical. Here, the population degenerates locally, so there are almost no particles, maybe only a few particles on the lattice in different points, and they continue its movement on the lattice. So there is no sense to talk about the spread of population when the population consists of several particles and does not grow. But it's interesting to discuss the problem of how far the particles can walk from the origin for the whole history of the process. So we introduce the maximum of catalytic branching random walk at time t, and then the maximal displacement for particles for the whole history, maximum for when t is positive, is any positive number. So, and we, our new results establish the asymptotic behavior of the distribution tail of such a maximal displacement. And it's interesting that it differs considerably from the known results for ordinary branching random walk, which is considered, for example, in the survey by Zanshi, which is maybe Bastien Malène will talk about in a day. So there are several results for critical and subcritical. Neumann-Jen for subcritical and Lally Shao for critical branching random walks. And there is completely another asymptotic behavior of such a characteristic. So we find a new effects which do not arise in a previous study concerning branching random walk without catalysts on ZD. Okay, I think it's enough. And at the end of the talk, list of our publication in this direction. So our results are published in these papers. And thank you very much for your attention, and I'm sorry for the delay.